Okay, so just a quick recap of what was the conclusion of the first lecture, just so that we have everyone on the same page for those who maybe dozed off at some point. So we will, for the rest of the lectures, be interested in understanding the properties of the eigenfunctions and the eigenvalues of this eigenvalue problem, where, so this is just free motion on, so free motion, I mean geodesic motion on hyperbolic space, and with specifically, well, I didn't write it, but with specifically the requirement that phi would vanish on these boundaries here. But for this, and of course we will be interested in the quantum problem of that, so trying to find the wave functions that satisfy this Laplacian eigenvalue problem. And although we're interested in the billiard, most of the whatever I'll be saying will apply to the fundamental domain of the modular group, which is also this, like these two things here. Maybe I should have used orange here and then white for the whole region here. Okay, so one thing I didn't mention explicitly is just to keep in mind what the action of the modular, of some of the modular transformations do on this domain. So the boundaries of the modular domain, which is this thing here, right? These boundaries get mapped into each other under some of the modular transformations. For example, this boundary here gets mapped to this one by the action of just a translation operator by one unit. And these two bits here and here, they get mapped into one another by the action of the modular transformation S, which is in matrix form. It will just be like this, okay? And in matrix form, the translation is nothing but this. Both have determinant 1 and only comprised of integers. Okay, so that's a quick recap. That's what we want to do. And for the first two lectures, well, the coming two lectures, we'll be mainly interested in the spectral properties of these Ks here, or more generally, you could say that these are the energies of the eigenvalue problem. So I'll go back and forth between energies and Ks, so between E's and Ks, but the E's ones are related to the Ks in that way. Okay, and so the last thing I said earlier in the morning was that we were looking at the spectral form factor as a probe of the spectral statistics of this system. And I was very fortunate that Julian gave you a crash course on some of these things. So I'll build on what he was mentioning in the context of random matrix theory to be more precise about how the spectral form factor is constructed in this case. Yes? I have to write bigger? Okay, thank you. Okay, so the main quantity, as Julian was saying, the main quantity that we will look at is the density of states. So in my notation, I hope this will not be confusing, but I'll use the letter D for that. And well, one way to put words into what this means is that in some interval E plus dE, you expect to find that many states associated with these energies. So in that sense, it's the density of states. And in particular, if you were to integrate it up to some, let's put primes here, up to some energy E, then you would have some counting function that counts the number of eigenvalues you have to this equation below the energy you put at the boundary of this integral. So let's say it starts at 0, and you integrate up to E, and then this thing counts how many of these eigenstates you find with the given energy below E. So another way to write it down would be to say that it is defined as having a delta function at every one of the eigenvalues corresponding to solutions of this eigenvalue problem. Right, and then of course when you plug it in here, you would hit it as many times as you have ENs below the value E, and hence you would be counting the number of eigenvalues you have below E. Okay, any questions? That will be the main ingredient we'll use throughout. So the main point of the lectures will be to try and find methods or to describe the tools that one can use to compute this guy for specific systems. This is known as periodic orbit theory, and the goal of this lecture is to introduce it and to try to make the first steps to try and compute it for this system here. Okay, so that's just, well, you could compute one-point functions of this if you wanted to, as in the various multi-point functions that Julian was mentioning. But that's not really describing anything universal about the statistics. So with the next non-trivial thing that you could do is look at two-point functions, like what Julian was hinting at here. But there's one difference with what Julian was writing here. So let me just first write it down. So we'll be interested in things like this, but whereas Julian was averaging over some random matrix ensemble, what we will want to do here, because we have a single system, we will be averaging over some energy window. So we will look at correlations or at the probability of finding eigenvalues separated by a distance epsilon at a given energy scale, and we'll be integrating over a small width about this central energy here. So that's a way to have some statistical ensemble, even though we're not actually in some random matrix model, by using the fact that we lump a lot of energies together, and this will give us some type of statistics to be able to work with. Okay, so that's a difference with what Julian was saying. Sorry, which one?
It's the left-hand side of what I wrote.
Yes, right. So, but I just mean that's for a specific model, and of course, if you want to describe it using or try to see similarities with random matrix, what random matrix theory would tell you, then you would have to do the ensemble in some random matrix model. Okay, so of course, you should be precise in what you mean with having this smoothing around some energy. I won't be too precise, it won't matter too much, but in principle, you have to do it. Okay. So, and then the next step, of course, to go to the spectral form factor, which I'll write again afterwards, is, as Julian was saying, to Fourier transform this in the value omega. And so let's wait immediately. And this gives you the spectral form factor. And as Julian was pointing out, because you're not imposing anything of the sorts of having some energy in between those two values here. So this probes correlations across the whole spectrum, as opposed to the level spacing statistics, which you would impose that does not have any energy lying in between those two. There is, I think, modulo some assumptions that you can make, or that you choose to make. There might be a way to link or relate this to the spectral statistics that would give you Poisson or Wigner-Dyson. But we will mainly focus on this, because otherwise you have to assume these assumptions, and I don't want to do this during these lectures, and I don't think I'll have time anyways. So we will mainly focus on the spectral form factor, and I guess there's one more thing I have to say, given that I mentioned that the spectral form factor that we were looking at was not quite this. I was mentioning something about the slope, that in what I'll be focusing on, the slope is not important. The way in which you get to this other spectral form factor the one that I'll be plotting, is by already hinting at periodic orbit theory. So if you write down the density of states, and as we will see, there is a sense in which this function oscillates about a mean value, which we will denote like this. And the remaining part will be comprised of oscillations. So we'll call them oscillations. And the whole purpose of periodic orbit theory is to try to compute this and to make sense of these oscillations. And these will be the guys that are related to the periodic orbits in the name of periodic orbit theory. So if for now you assume that something like this holds, so the whole point of the next lectures will be to try to understand this guy, specifically for this system. But if for now you assume that this is something that you can do, you plug that back in. We will define, maybe I can just write it like this. So we will be specifically looking at the two-point function of the oscillatory part of this guy. Again, I guess it's sort of, I was already mentioning the fact that the one-point function of the density of states are not the relevant thing. So this guy is something that in some systems you can compute or you can predict analytically. In billiards, for example, you can just find a formula for these guys using periodic orbit theory. But this is not what contains the interesting information in the spectral form factor. Like the ramp and the plateau and so on, it's really, well, I guess mainly the ramp, it's mainly about this oscillatory part. The plateau, let me mention it just now, the fact that we have a plateau is intimately related to the fact that you have a discrete spectrum. So in any discrete spectrum, you will have the spectral form factor will asymptote to a plateau value. And that's also why it's really, well, like this plateau value was related to this averaged density of states at some energy. So again, this, while we're not necessarily writing it down, this is always related to the energy you're considering this two-point function at, and this energy has been Fourier transformed, so it's only a function of the time conjugate to that energy. Okay, so let me just plot these things again now that we have the definitions, and then the whole point will be to try to understand the curve for arithmetic systems. Okay. I guess I should have maybe left a bit more place here. Okay, so for, say, integrable models, the curve was going like this. So it's really sort of zero here at a time t min, which was the period of the shortest periodic orbit. So that's integrable. For arithmetic chaos, you would have something that grows exponentially. With the energy, sorry, this should be a k. And then in the semi-classical regime where k is very big, you would have something that jumps towards the integrable curve as quickly as it can, basically. So that's. And then, this point here, well, maybe this has some oscillations as I was saying before, but roughly this time scale here is known as the Ehrenfest time, and this went as the log of k over k. So as k goes to infinity, it goes to 0. And then in the chaotic or the GOE or the GOE cases, it would have this linear ramp and would only saturate at a much later time scale, which is known as the Eisenberg time scale, and which is which goes as which is set by the distance between neighboring eigenvalues, the average distance. Okay, so there's different timescales that are in the game, and here this would be a linear ramp, and that's what you often hear whenever people talk about the spectral form factor of chaotic models. Okay, so is there any question about this? So the point now is I want to discuss periodic orbit theory because I think it's a beautiful topic, and I have to warn you, it is a tiny bit technical, but I think it's a beautiful topic. You can apply it for these systems, but for like generic chaotic systems. Of course, you have to have some knowledge about periodic orbits, but the point is that for long periodic orbits in chaotic models, you expect that the behavior of these orbits will follow some generic behavior, and hence you can derive some things such as the linear ramp, making some assumptions. And so it will be interesting to see exactly where the difference lies for arithmetic systems. And I can already tell you the important words. The main difference between arithmetic and chaotic systems is understood to be precisely in the periodic orbits, namely the fact that that this modular domain here, or that the billiard domain is related to the fundamental domain of SL to Z. You can show, and that will be part of the things that we will show, you can show that there is an exact degeneracy of the amount of periodic orbits of a certain length. And this number, so the degeneracy of periodics of a certain length, grows exponentially with the length. And that's a very unusual feature. And that is basically what leads to this exponential phenomenon here. And that is not present in usual chaotic systems. So the whole point of what we're going to do now is to show this fact and to show how it enters using periodic orbit theory into the computation of this spectral form factor. Okay, any questions? Yeah.
Maybe just looking from this figure, is it okay if I call arithmetic system to belong to a different class and not really chaotic?
Well, okay. So I guess the important point is that in deriving the spectral form factor, you're making some assumptions about, for example, how, like the periodic orbits and how they profilorate and so on. And this behavior is just different than arithmetic systems, and we will see how and why.
So is it okay to call them neither integrable nor chaotic, but something which, let's say?
Well, if you like classifications, I guess you can call them whatever you want. But the main point is to try and understand where they differ. And that's I mean, to me, that's the most important point.
Wasn't it mathematicians who came up with the name?
Say again, sorry?
Wasn't it mathematicians who came up with the name?
With the name arithmetic chaos? I mean, arithmetic just comes from the fact that this domain is related to the SL to Z and the Z in SL to Z. And we should always blame mathematicians. Yeah. Okay. Yes.
Some random matrix analog which present the same spectral form factor?
No, so I think, to my knowledge, there's no other system or there's two systems. To my knowledge, there's no other system that displays this type of behavior except those that we understand belong to this class and have these arithmetic properties and so on. And then regarding models like ensembles of like matrix ensembles, I don't think so. I haven't heard of any. Yeah. Any other question? Okay. Okay, so then we'll jump, I think, to understanding. Oh, there was one more thing I wanted to say. So, to be specific, to have an idea of what I was writing here about the split of the density of states into some mean part and some oscillatory part, let me just give you, so this can be done, I think I never ended the sentence I started with when I was saying that this can be done for integrable, for chaotic, and for these models. Actually, well, I think it would be fun if during the tutorials we could go through an integrable example where we were to compute some things just for you to get some feeling with it. But let's see how things go. In any case, I think in the notes I'll put it as an exercise because it's a very nice thing to try and work out. But let me write down the trace. Okay, so these things are called trace formulas. The name should be clear at some point, but it's not clear yet. But let's write it down first for chaotic models. So the generic version of this formula. And you can write a similar formula that looks slightly different for integrable models. Okay, so these type of formulas, I'm not going to tell you how to derive it, but for the arithmetic case or on hyperbolic domains, we will go through the derivation. So that's what is going to be the technical bit of the lectures. You can derive a similar formula for generic chaotic models that have nothing to do with motion in a hyperbolic space. For example, for billiards in Euclidean space, you can write down some trace formula, which is known as the Gutzwiller formula. But it is important to remember that this formula, while you can derive it, it's only valid semi-classically. So say high energies or small H Planck value. And the reason for this is just because it was derived using this approximation. So it's derived using lots of stationary phase approximations where you're assuming it's about to be small and so on. So it's only valid in this approximation, whereas the formula that we will derive together for hyperbolic spaces has a feature that you're never using, at no point are you using semi-classical assumptions, so it's just a valid formula which then goes by the name of the Selberg trace formula. So it has different names that have different domains of validity, but usually the spirit is the same in both cases. The derivations are, can become lengthy. Okay, so in that framework, you can write down a formula for the mean energy density of states at some energy. And suppose you're in f dimensions. Maybe I should just use, okay. I would use D, but obviously D is used for other purposes. And it looks like this. So I'm not going to comment much, it's just to write down what it looks like. The most important thing is not this guy, but it's the oscillatory part, which we will care about and which we will plug into the spectral form factor as well. And this one goes by a sum over periodic orbits. So usually, if you have one periodic orbit, say, suppose you have a billiard, suppose you consider one of the periodic trajectories. Of course, if you consider this trajectory twice or 3 times, they're labeled, they all enter this formula. So what we will use to label them is just what is called the primitive periodic orbit. And so that's the first one, where you go once around the periodic orbit, and then the other ones will basically just get a factor of n for all the times you go about that orbit. Okay, so that's primitive periodic. Oops. By the way, is the size better? Because I don't think I. Okay. Yeah.
What is the superscript of the D, and what does it mean?
Oh, that's oscillatory. So the mean part. It's what it means. It's the mean part, like the average behavior of this function. But then there will be oscillations on top, and oscillations are understood via periodic orbit theory, and that's the formula to compute them semi-classically for any chaotic system. Okay. So let me just write it down, and then I'll go through the various, whoops, some. Okay, so the details are not important. I just want to give you a feeling for what it would look like and what are the ingredients that enter, so that whenever we compute it for the hyperbolic case, that we can identify the various things. Okay, so this is the period of the primitive periodic orbit. This is the determinant of some matrix called the monodromy matrix, which describes the stability of the periodic orbit. So, okay, so we'll see how it gets, like what it looks like in the hyperbolic case, or at least for the orbits that we will consider. And then this guy here is a cosine of, so this is the orbits that follow from this periodic orbit taken in multiple times, so that is this number n. These things are called Maslow's index or indices, and they describe, like in a billiard, for example, how many turning points you have. We won't care about it, it won't be important in our case. And these are the actions of the corresponding periodic orbit. Okay, so that's what it looks like. And as I said, you can derive it using semi-classical methods. Well, okay, I mean, to me, whenever I was learning about this topic, I found it crazy that you could use classical data, namely these periodic orbits, to try and say something about fluctuations in the spectrum. Because usually what you're told when you're learning about classical quantum correspondence is that you can start with some quantum theory, go to the semi-classical limit, and find a classical theory. But I guess nobody really tells you that there's actually some interplay going the other way as well, which I think is beautiful. Okay, so
What is TP and P here?
TP is a period of the periodic orbit. Any questions? So that's what it sort of looks like, and the aim is to try and derive the analogous thing in the hyperbolic case. And of course, the first thing we'll do then is try to understand the periodic orbits on this manifold. So that's sort of why I was telling you about the fact that, like, the action of the modular group on the boundaries of this domain, because it will be sort of important to realize at least that although we're interested in the billiard, where geodesics would bounce off of the billiard, in the case of the modular domain, which is the thing we'll be focused on first, and hopefully I can say some words about the billiard. But in the case of the modular domain, when a geodesic hits this point here, what happens is that you have to map whatever was here back to the modular domain. So using, say, a translation in this case, it will bring you back here. So you have periodic boundary conditions. That's not reflection boundary conditions. Okay, so that's something important to keep in mind, because now we're going to try to understand these periodic orbits, and they're basically very well understood, and you can say a lot of things about them. So that's what we're going to do now. Okay, so I guess it might be common knowledge, right, that geodesics on the upper half plane are just either they're straight vertical lines, or they are semicircles that are described by the following equations. So the semicircles that hit the y equals 0 axis in the middle, so they look like this. Okay, hopefully this is common knowledge. If you don't know this, this is something you can just derive by computing geodesic equations in the hyperbolic background in these coordinates. Okay, and so you can show that for elements of the modular group, oops, I forgot the S. For elements of the modular group, there's different type of elements. The elements for which the trace is bigger than 2, you can show that they leave, well, for each of these geodesics, you can find a transformation in PSL2R so that this geodesic remains invariant. So that means that not necessarily every point on this geodesic is mapped to itself by G, but there exists a point on the geodesic that maps to another point on the same geodesic using this G. So there's many such G's for a given geodesic, but importantly, the endpoints, given the G that leaves this thing invariant, the endpoints will remain invariant. So while other points on the geodesic will be mapped to other points on the geodesic, the endpoints remain invariant. And if you try to solve for what does the matrix G element of PSL2R look like so that a specific geodesic with x0 and r remains invariant, you can do the computation if you want to, and what you find is that the entries of some G, A, B, C, D will be related to x0 and r in the following way. So here I'm removing the b, so I decided to express the b, the function of the other two, by using the determinant condition. Okay, so any G that looks like this, that given these relations give you a given x0 and r0, will leave this geodesic invariant. That's just a fact. That's something you can check for yourself if you want to. Note that this condition here enters the fact that this r has to be positive, so you require this to be bigger than 2, and this bigger than 2 means the trace of the matrix needs to be bigger than 2. Okay, well, that or, of course, I won't go into the details, but if it's negative, it also works, but we're going to remain positive for the moment. Okay, so that's true for, like, given any of these values, x0 and r, you can find G's in PSL2R that leaves them invariant. Now, the claim is that the geodesics, the closed periodic orbits in this domain are precisely related to G's that belong not to PSL2R, but to PSL2Z. Okay, so that's what we want to show now. And the way this goes is that suppose we have a geodesic. I'm just drawing a random thing, and okay, maybe it's not the best drawing in the world, but the point is that whenever it's not in the domain anymore, what you have to do to find what it looks like in the domain is find, for every such point here, you have to find the matrix in the modular group. So where the modular group, I mean PSL2Z and not PSL2R. So you have to find the matrix in this group that brings it back inside. Okay, and if you have a periodic orbit, what happens is that there will be a point along this curve which is mapped back to here, and basically this segment here will be mapped exactly to this segment here. Right? That's what it means, because then if you were to map, say, those would be other segments that you would have in this domain if you were to bring them back. If you have one that falls on top of this one, then you have closed periodic orbit. Does this make sense to everyone? Because it's sort of crucial. So, okay, you can also think about it a bit later, but the main point is that for a periodic orbit, you need to have a segment that falls back onto the original line that belongs to the geodesic you're looking at inside the modular domain. And if you can do this, then that means that, in fact, this geodesic, or this segment here, this geodesic is left invariant by a matrix in PSL2Z and not in PSL2R, right? Because you're falling exactly on top of this geodesic anymore. So this geodesic is left invariant by the G that you needed to bring this thing back here. And this G, because it's a modular transform, belongs to PSL2Z. Okay, so yeah, you can play this argument. Like I didn't use much, right, in this argument. I just used the fact that for it to be a periodic orbit, there has to be a segment that, when it moves back into the fundamental domain, falls on top of it. Then you have a periodic orbit, and precisely this means that this geodesic here will be left invariant by some element in PSL2Z. So we get to the statement that a periodic orbit in H2 mod the modular group is in one-to-one correspondence with, well, leads to the fact that you can find a G in the modular group, whoops, that leaves it invariant. Okay. But the question is this the only element of the modular group that leaves it invariant? Of course, this line, it will be the only one that leaves it invariant, modulo, of course, G to the power whatever, n, because then it just leaves it invariant, and so on, multiple times. But you can express the geodesic that would be written in the fundamental domain. Like I could, for example, say, okay, this guy here, if I want to map it back, well, okay, it's badly written, but say if this is 3/3, then I would have to translate this back here, right? And then it would be like this bit here would be translated back here, and you can do this for all the bits. Let's look, for example, drawing is very messy, so tell me if it's not working for you anymore. But you could try to continue this geodesic and ask, given if I focus on this bit inside the modular domain, which is the geodesic, which is the matrix in the modular group, which leaves this matrix, which is the matrix in the modular group that leaves this part of the closed orbit invariant. And, well, the answer is sort of easy. You needed one translation, say t-1 or something, so you translate it back one time. And then, given that you know which matrix element, this one, leaves this curve invariant, you know that whatever leaves this curve invariant, okay, let's say we look at the geodesic, I'm calling gamma here, is this one. I apply some translation to it so that it becomes this one. I know that this one is left invariant by G. So I know that G T gamma is nothing else than T gamma. So in particular, the sorry, I'm imagining confusing myself. I'm just going to think straight for a second. Okay, so the claim is that this geodesic, the claim is that this matrix leaves this geodesic invariant. Okay, so we're going to check it. So we want to check that right. We want to check that something like this holds. Okay, so we know that this guy was invariant for G, right? Because if we map this back to here, we get the invariant geodesic for G, right? Okay, so we're there. So T minus 1 we're using that G leaves this invariant, so then we get this and we get this. So we showed that indeed, sorry for being slow on this, so we showed indeed that this matrix here leaves the new translated geodesic invariant that brought this bit here back to the fundamental domain. So this shows that for a given periodic orbit inside the modular domain, there's actually many geodesics that will correspond to that. So there's many matrices that correspond to that geodesic. Namely G, as we showed with the first one, but also all the geodesics that belong to the conjugacy class of G. So a better statement here is that a periodic orbit in this domain is in one-to-one correspondence with a set with a conjugacy class, well, okay. Instead of just one element. Okay. And of course, this conjugacy class has to be considered within the modular group, because the T that we use here in this example was nothing but the transformation within the modular group that was needed to bring it back to the fundamental domain. So you can, there is a one-to-one correspondence between periodic orbits and conjugacy classes of,
Sorry.
yes?
T is just something that keeps the shape of geodesic invariant?
You said T, or? No, T in this example was just to do the easiest one for this specific geodesic. So here T I was mentioning.
What I'm saying is it something that leaves the shape of geodesic invariant coming from symmetry?
So what, okay, this T in particular is a translation operator that would bring this bit back here. So what it does, it translates all the points along this line with one unit to the left. That's what it does. And it belongs to the modular group, and its matrix is written like this. So if you write out the action on Z, you can see there's just a shift by one unit to the left. Now here, this was just an example. Like I could have done the argument for a generic bit of this geodesic that has to be mapped, maybe using like multiple T's and multiple modular transforms to get mapped to the modular domain. But I managed to confuse myself even with T, so let's not try to make it more complicated. But the argument goes exactly the same way. So you have to do this type of manipulations, and then you see that the way to keep the matrix that keeps this geodesic here that was mapped from here to here, matrix that leaves this geodesic here invariant, is nothing but the thing that you have to translate back. Use the fact that it was invariant and translate again to the original thing. And then you find that it's conjugacy classes that determine one periodic orbit and not a single matrix. Okay, so there's one more thing I want to discuss before stopping, and let's try to make it short. Given now that we know how to connect periodic orbits with conjugacy classes, what we want to show now is that the length of the period of the periodic orbit, so the length of the periodic orbit there is a simple relation between that length and the trace of the matrices that leaves it invariant. So notice that conjugacy classes, they all share the same trace, so it makes sense. Okay. So the argument is quite simple. It uses the fact that given a periodic orbit, say we take this one, there is definitely a matrix in PSL2R that maps it back to, say, this geodesic here, which is just the vertical geodesic that lies at x equals 0. So it's basically the statement that you can use you can use transformations, these fractional linear transformations, to map any geodesic into one another. And if you do that, well, the whole point of the first argument I was giving to show that a periodic orbit was related to a matrix G was the fact that for every Z along this geodesic, G of Z is equal to, there is a Z, right, for which, let's draw it here. So there is a point, I think we put it here. So there is a Z which, when applying G to it, will get it back here, right? Okay. And in particular, the distance. So we're interested in knowing the distance between this point and this point, because when mapped back to the modular domain, it will give you precisely the length of that periodic orbit. Right? So we're interested in the length between, so that would be G of Z, and that would be Z. So we're interested between the length between Z and G of Z. Okay? But now we map this geodesic to this vertical line, which makes the computation of length between points very easy. Okay, so let's say we start with this geodesic, we map it back to this point, and say this was Z and this is G of Z. We can really take any Z along the geodesic, it doesn't matter, right? And then using this, let us maybe call Z prime so that you're not confused with the G's that leaves it invariant. But so under G prime, the only thing that it does is it maps it to an easy geodesic. The real shape of this G prime is not important, right? What we care about is the G that leaves it invariant. And then maps this point to this point, and we're interested in computing the length associated to this G. Okay. Right. So the only difference between these 2 points is in the y direction, right? So it's enough to use the geometry of the hyperbolic space and integrate only in the y direction. And this in particular will okay, so under this G prime, this matrix here, which was not diagonal, will be mapped to a diagonal matrix. Why? Because this shape is precisely what leaves this vertical geodesic invariant. So, okay, we don't have to be precise about the shape of this J prime. We just know that it will diagonalize this matrix, precisely because the resulting geodesic is a vertical line at x equals 0. So then, you know how this matrix here maps the z-coordinate, namely, it maps it in the following way. So that means that both x and y get scaled up by this factor lambda squared. So in particular here, you know that you can write lambda squared y and y, right? That's we're after the distance in the y direction because the x direction does not change. We're after the y direction change as you apply this matrix G mapped by this G prime to a diagonal form. Okay. So then this integral is super easy to do, right? Like so the y here comes from the hyperbolic geometry, right? So then this is log the y's will drop out, and you find this length for the period of the periodic orbit. Okay, so I'm using length and period interchangeably. Of course, there's maybe a factor of the energy in between, but I'll be precise when we need to. And so what that means, let's write it a bit neater. So you have this relation, right, using this equation. And so you find so you can do a bit of algebra and show that this is true. Okay, didn't do anything crazy. And now you can have a look at this matrix here, and lambda plus lambda inverse is nothing else than maybe I should just give it a name, I don't know. Okay. So this is nothing but this matrix rotated according to this guy, and the trace of this here is equal to lambda plus lambda minus 1, but it's also equal to the trace of G. Okay, so then what you find is that 2 times the cosine hyperbolic of the length of the periodic orbit is equal to the trace of G. Okay, so in this way, you can relate lengths with the traces of the geodesics that leave it invariant. And of course, you could have taken any of the G's in the conjugacy class that leaves this periodic orbit invariant in the fundamental domain, because they all have the same trace. They're part of the same conjugacy class. Okay, so now comes the important point to notice, and I'll close there. These traces, they cannot be arbitrary, right? We're dealing with matrices in SL2Z. So in particular, A and D that make up the trace are integers. So these will be elements of n, n, and in particular it's bigger than 2. So periodic orbits, I should have, maybe if you're taking notes, I should have written here hyperbolic conjugacy classes, and hyperbolic just means that the trace needs to be bigger than 2. So in particular, the lengths of the geodesics are not at all arbitrary. They have to be related by this cosine to natural numbers. And well, okay, in principle it's C, but okay, let's not complicate things. So it has, and that's where arithmeticity is coming from as well. the fact that these traces, the lengths of these geodesics are not arbitrary, but are drawn from a very discrete set, basically. Okay, so, okay. Please come and ask me questions if any of this was too confusing. And, well, thank you and see you tomorrow.
Is this length or a cycle?
Sorry, what?
Is
D?
cycle?
No, it's the length. So what we're doing is computing the distance between this point and this point, which under this G are mapped into one another. So it's the length. We're using the metric to compute this.
It also looks like some cycle or some Riemann surface.
Are you saying cycle?
Yes.
I'm not sure what you mean cycle.
Some homology of Riemann surface.
Some what?
Homology class of some cycles on Riemann surface.
Are you saying because of what part?
Yeah, because.
Oh, because of this?
And also it's divided.
Yeah, well, I'm not familiar with the words you're using, so I wouldn't be able to tell. But yeah, the only thing I can say is that this length is just using the metric. We're computing the length between 2 points, so the length of the periodic orbit that is associated to G.